So you got 4.16I minus 19.56J, which means he's going 4.16 miles per hour horizontally. He's going 19.56 miles per hour vertically. All right, ladies and gentlemen, today we are looking at modeling with vectors. Now, we slightly started this yesterday because vectors have a lot of real-life applications. And yesterday, when you were finding a vector based off its magnitude in this direction, remember, I kept on asking its horizontal speed and its vertical speed. That's one of the first applications of vectors. Another one is to talk about positions and distances. And this is example one. You already have this in front of you. It says, while golfing, you drive a ball into the woods. The ball ricochets off a tree at a 90-degree angle and lands into the fairway. Your shot can be modeled by this vector. The ricochet off the tree could be modeled by that vector. And then we got to draw it in the coordinate plane and go from there. And if you don't have a piece of graph paper, get one. You're doing it on that piece of graph paper. It'll look prettier. Trust me. I'm waiting for you to get it. All right, so let's start. You know what? You're going to start here. You. And then it says your shot can be modeled by U equals, or sorry, that's a V. V equals 12, 14. So we know we got to go right 12, up 14. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. When we think about it, that's where the tree is. Because didn't it say then your ball ricocheted off a tree? So we got to show that you went, your shot went there, hit the tree, and then from there it could be modeled by -7, 6. Well, we're going to -7, 6. And we got to start here, and then go -1, 2, 3, 4, 5, 6, 7, and then up 1, 2, 3, 4, 5, 6. It's right there. And if you think about it, look at that. That even made a 90-degree angle. It even looks like it. Now, first thing, draw this in the coordinate plane. You just did so. Second thing, find and draw V plus W. Well, you could find V plus W, or you could draw V plus W pretty quick. You knew that this part was V, that part was W, so connect the dots. Then V plus W is going to start there, and right here, there's V plus W. You've drawn it. Now to find it algebraically. Well, remember, we can always add things component-wise. So we know that we can add the 12 plus -7 and get that. Let's see, what part B? V plus W. Well, 12 plus -7 is going to be 5, comma. And then if we think about it, we got to go 14 plus 6. Well, that's 20. Well, look at the V plus W vector, going from where you started to where your ball ended. Well, if you think about it, you just went right 1, 2, 3, 4, 5, and you went up 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we know we did that right. Now for part C. It says find the distance in yards of the ball before it hit the tree. Now think about it. Think about it for a second. Which vector was the ball before it hit the tree? Was that V? Was that W? Or was that V plus W? That was V. So, if you want to know the distance, then we got to do the magnitude of V. You know? Let's think about it. The magnitude of V. Well, if you thought about a triangle here, think about a triangle there. Well, let's think about it. This part's 12, that part's 14. Do the Pythagorean theorem. 12 squared. That's 14 squared. Equals, we don't know squared. That's 144 plus 196 equals r squared. And then 144 plus 196 is going to be 340. Take the square root, and you get 18.44 yards. So that means your shot with 18.44 yards before it hit the tree and it started ricocheting. Now for part D. Find the distance in yards of the ball after it hit the tree. So now you got to think about right here. Starting up there. Starting up here. And going across there. Think about that. That was 1, 2, 3, 4, 5, 6, 7. That was 1, 2, 3, 4, 5, 6. So set up in your Pythagorean theorem. 7 squared plus 6 squared equals we don't know squared. 49 plus 36 equals we don't know squared. 49 plus 36 is going to be 85. Square root. Square root. And the square root of 85, I know it's bigger than 9. How much bigger than 9? No, not bigger. 9.22. So we know that that part is 9.22. So if I wanted, I could label this part with a 9.22. I could label this part with an 18.44. And notice the whole time we're talking about position. So that's why those were distances and not speeds. Now, next part, let's see, we did D. Now we need to do E. How far in yards are you going to walk to get your ball? Well, honestly, guys, I've got a couple options. The option I like by far the best is how far in yards are you going to walk to get your ball? Well, that's the B plus W vector if you think about it. Because your ball got shot here, ricocheted there, you got to walk from here to there. So, figure out the Pythagorean theorem on that triangle now. So, let's drop him down some more. Whoa, that's going to be a 5. That's going to be a 20. Go ahead and count it. Now let's plug it in. So for E, 5 squared plus 20 squared equals, we still don't know squared. That's 25. That's 400. We don't know squared. 425 equals r squared. Square root. Square root. And I got 20.62 yards. So to answer the question, how far in yards are you going to walk to get your ball? Well, you're going 20.62 yards. So there's a couple examples of how magnitude might be used. And now for part F. Find the measure of the angle formed by the path of your shot before it hit the tree. The path of your shot before it hit the tree. And the path you walked to get your ball. That one right there. So if you think about it, you're trying to find your theta right there. Now this part actually doesn't use any vectors. This is an old geometry problem, guys. Think about it. You've got a couple different options here. You know that that part's 18.44. You know that part's a 9.22. Very subtle detail in the problem. Ball ricochets off the tree at a 90-degree angle. You are 90 degrees, sir. And then we know that this part is 20.62. Quite honestly, guys, I don't care which trig function you use, just get it right. I'm going to pick, what am I going to pick? I'm going to pick sine. Why am I picking sine? I don't have a reason. I can use any three of them. So, part F. Sine of we don't know equals opposite is 9.22 over hypotenuse is 20.26. Sorry, 62. So we know that sine of theta equals 20.22 divided by 20.62. And then take the inverse sine. Now honestly, I'd rather just take the inverse sine of that big old number. So second inverse sine. And I got 26.56 degrees. Theta equals 26.56 degrees. So to answer that last problem, part F, what angle was formed by the path of your shot and the one you actually had to walk? 26.56 degrees. Another application of vectors is to talk about how forces can act upon something. Because the way that forces act upon an object act the same way how we add vectors. So that's why I have force 1, force 2, and what's called the resultant forces. And that is once we add the vectors to talk about what force, after we combine them, is happening upon this object. Now, there are a couple other little things that I want to talk about before we get to the next two examples. There's a couple things you probably haven't seen in a while. First thing, directions. North, south, east, west. We know that. direction angle, remember we talked about direction angles a lot. The direction angle has to be 35 degrees. So really quickly, think about it. If I say southeast, what direction angle am I really talking about? Take the next couple seconds, try to figure it out. If I'm talking about southeast, what's the direction angle I'm really thinking about? Think about it, guys. This has to be 45 degrees. Well, you know that's 360. So 360 minus 45. Then the direction angle I'm talking about, if I do southeast, is 315 degrees. That's the next thing. One more thing. Let's say that you're on a boat. Just real quick, you're on a boat. And, well, you need to explain to somebody that you're going this way. Well, first thing, start with your main direction. Now for us, let's say the reference angle, just for the fun of it, is like 78 degrees. Now if you look, the main direction you're going is south. So the way you would describe this is south, and then I know you're going kind of west. Well, you need to tell me how much west. It's not going to be 78, because you got to tell me how much west. So you got to tell me how much you're going that way. Think about it. That's going to be 12. So then he's out of 90. So I make 80 plus 10, yeah, 90. So then you would say it's south, and then 12 degrees west. That's how you would tell me that portion right there. Now, for the next one, let's say that it's this. And let's say that you were going, let's say, that way. Let's say this time everything was 10 degrees. Well, the main direction you're going is that way. Well, that way is west. And then you got to tell me how much you're tilting to the north, because the north is up that way. If we were going that way, it would have been the south. Well, you're going north 10 degrees. And that's how you would state both of those. So just to reiterate, your main direction was going first, because we were going south mainly and west mainly. Your second direction tells me kind of how much you're tilting. Well, you were tilting 12 degrees to the west. You were tilting 10 degrees to the north. Now let's take a look at example 2. An aircraft maintains a constant airspeed of 500 miles per hour, headed due south. The jet stream is 80 miles per hour in the northwest direction. First part we're going to do, we're going to express the velocity vector v sub A for aircraft, in relation to the air, and the velocity vector v sub W for the wind of the jet stream in terms of I and J. Now one thing I want to tell you, this is going to be the last example you ever see the word vector, you ever see the word vector. They're just going to say express the velocity VA, and they have to assume you know that means it's going to be a vector. And then, and the velocity VW, they're going to assume you know it's a vector. Okay, the last example you're ever going to see those words. Well, let's start with part A. Express the velocity VA of the aircraft in relation to the air. Well, think about it. What is the aircraft doing? Look in the problem. The aircraft is headed due south 500 miles per hour. Here's what I do real quick. Draw this tiny picture. If I'm going due south 500 miles per hour, well then think about it. If you're going south, that's a negative in the vertical direction. Vertical. Is that I or is that J? Think about it for a second. Vertical. It's going to be J. And we went down 500. So for the velocity vector v sub A, well, v sub A equals negative 500J. Because we're going due south, negative 500. So then just to make sure I'm making sense, if instead it had said it was going 600 miles per hour due west, well, due west is that way. So it would have been the I direction, and it would have been negative. So I think I said 500, didn't I? So negative 500I. Now remember, that was different than this example. This example, you're going due south. That's why I picked J. Now, next part. It says, find the velocity vector v sub W of the jet stream in terms of I and J. Well, look at the jet stream. All I told you is that the jet stream is going 80 miles per hour in the northwest direction. So think about it. This is like the problems from yesterday. They didn't tell us the vector. It's not going to be that easy. We're going to have to do some work. So think about it. Draw a vector that's going in the northwest direction. Well, northwest is going that way. And it said it's 80 miles per hour. Well, then that's the magnitude. from yesterday, well actually, hold on, I'm getting too far ahead of myself. Northwest, remember, you know that's 45 degrees, but that's not the direction angle. The direction angle goes the whole way around. That's 135 degrees. So that's going to happen to 180. Now let's plug it in. We know that V sub W equals, remember from yesterday, magnitude of V sub W times the cosine of alpha I plus the sine of alpha J. Well, we know that the magnitude is 80 because that's how fast the wind is blowing. And then the cosine of 135 degrees I plus the sine of 135 degrees J. Well, then that's going to be 80 times, so the cosine of 135 is definitely negative, root 2 over 2. I plus root 2 over 2, the sine in the second quadrant is positive, J. Distribute the 8 real quick. Equals, 80, I apologize. 80 divided by 2 is definitely 40, so negative 40. Root 2, I, plus 80 divided by 2 is still 40. 40, root 2, J. And now you've got your velocity vector with respect to the wind. Now for part B. Find the velocity vector V sub G of the aircraft related to the ground. There's supposed to be a related. Now wait a minute. If it's the velocity vector V sub G of the aircraft that's related to the ground, then we're going back to here. This is the resultant forces one. Because we need to know how much is the wind acting on our plane. Well, look here. It says whenever you have multiple forces, you got to add. So we know that V sub G, we know that V sub G equals V sub A plus V sub W. Think component-wise. Well then, if it's V sub A plus V sub W, well V sub A was negative 500J. So the only thing we're going to combine that with is the other J term. V sub A doesn't have anything in the i's, so leave the i's alone. Negative 40 root 2I plus, and then think about it. They both have J's, but they're not like terms. So put them in parentheses. 40 root 2 minus 500 J. Because 40 root 2 is positive. If you think about it, adding negative 500, the same as just saying you're going to subtract it. And that's the velocity vector with respect to the ground. The biggest thing you had to recognize is that they wanted you to add. So make sure you mark on part B. If it's talking about the velocity vector of the aircraft in relation to the ground, it's talking about adding the forces. We need to know how much that plane is being affected by the wind. And although that looks complicated, it tells us how much the plane is being affected by the wind. Okay, cool. Then, for C, find the actual speed and direction of the aircraft in relation to the ground. So, if you think about it, we need to know the actual speed and the direction. And there's two things we need. We need to know, well, speed. That's going to be magnitude. Two, direction. That's why I made a big deal about the direction and stuff yesterday. So, here's my advice. From here to do part C, let's transfer this into decimal. Things are going to go way better. So V sub G equals, let's see what 40 times root 2 is. 40 times 2 root equals, it should be negativized. So negative 56.569. And let's see what that's going to come out as. I'm thinking it's going to come out negative, because 40 times 2 root is nowhere near 500. Yep. Minus 500 equals, oops, let's do it right this time. 40 times 2 root equals minus 500 is, I got negative 443.43. So minus 443.43 J. Transfer it over to the decimals because for the actual speed, we're thinking about the magnitude. So, well, think about it for a second, guys. If we want the magnitude, draw this real quick. Just a base sketch. If you think about it, if it's negative 56.569I, that's going in the horizontal direction, negative 56.569. think about it, that would be negative 56.569. And then when you go down, negative 443.43, you draw your vector. And then think about the triangle you would have made. The triangle you would have made, gone down here, and that would have been negative 443.3. When you cross there, and that would have been 56.569, or negative right there. And use the Pythagorean theorem. So negative 56.569 squared plus negative 443.43 squared equals, we don't know square. Just keep on going. 56.569 squared plus 443.43 squared equals, big number. I was getting something like, just to double check you're on the right track, 199,830.22 equals r squared. Take the square root. Now it's getting 447 equals 0.02. So to answer the question, first part, find the actual speed. Well, the actual speed of the aircraft is 447.02 units. Units for miles per hour. Miles per hour. Boom. Now to answer the last part of the question. Last part of the question said, and direction. So we got to do the direction angle from yesterday. So remember, use tangent. By far your best bet. Use tangent. So, you know the tangent of theta equals, because this guy's going to be theta, or act like it. Because remember, the tangent is going to give us the reference angle anyway. Opposite over adjacent. So opposite is negative 443.43 over negative 56.56. And then take the inverse tangent, and you're going to get theta equals. I was getting 82.73 degrees. Now, 82.73 degrees is this part right here. Here's the catch. This is the part that I made a big deal about how we name things. The main direction you are going is south. So we know you are going south. Now, you're tipping a tiny bit to the west. Question is, how much to the west? Well, you know that's 82.73. Almost subtracted from 90. You know, it's getting 7.27. So south, 7.27 degrees to the west. And you're good to go. Alright, here's your answer for you try. The velocity of the airplane should have been 900J because it was moving 900 miles per hour and due north. That's why it was J. And then for the velocity vector of the wind, well, you know it's 120 miles per hour, so that's its magnitude. I said it was going northwest. So northwest. That means the direction angle is 135 degrees because that's the reference angle of 45. Plug it into the formula from yesterday. Cosine 135 degrees I plus sine 135 degrees J. Simplify it, and you should get negative 60 root 2I plus 60 root 2J. Now for the velocity vector with respect to the ground. Well, remember, that's the resultant forces vector. So you need to add the airplane and the wind. And that's what I did here. And if you look, all I did was combine like terms. That was a J, I added it with the J. Whoops, wrong J. That J. And you get this. Now for the actual velocity of the plane. Remember, that's the magnitude of the resultant forces vector. So I graphed it real quick. And I did the Pythagorean theorem. And you'll get that it was going 988.5 miles per hour. Now remember, the last part is we got to get the angle that it's going at. Well, I looked at the triangle again. And I was thinking, well, that's going to be over here, the 984.85, and then negative 84.85. Use the tangent. Well, remember, when you take inverse tangent, it's only defined in the first and the fourth quadrant. So that's why it came out negative 85.08. The tangent was negative. So it's going to pop out in the fourth quadrant. But remember why I said it was awesome to use tangent. It tells you the reference angle. The reference angle is 85.08 degrees. So put it back in the picture. And then you look, and it's going majority north. Because it's going up here. But then it's going a tiny bit to the west. Well, how much to the west? subtract the 85.08 from 90. It's going 4.92 degrees to the west. So the next couple of examples we do deal with something called static equilibrium. Now, what that is when the sum of all the forces on a vector, they must equal zero. In order to be at static equilibrium, equilibrium is what hence means. It has to equal zero. Now, what this means is that if it's going to equal zero, then think about it. If you have a zero vector, then the I component has to be zero, and the J component has to be zero. Usually it's going to require a substitution. Now remember that from algebra. And the last part is, just for these types of problems, remember how speed showed us magnitude when we were dealing with the plane problem? Well, for these, weight or tension is going to be magnitude. Alright, example 4. A box of supplies that weighs 1,200 pounds is suspended by 2 cables. What is the tension of each cable? Picture looks like that. Well, for tension, remember, meant magnitude. So we're looking at, well, what's the magnitude of that cable, and what's the magnitude of that cable? Well, the catch is, first of all, we have a third force acting here. We have our third force of the 1,200 pounds dragging everything down. Well, we got to check when this thing is going to be at static equilibrium. And remember, static equilibrium is when all the forces add up to equal zero. Well, let's start by labeling the forces. Let's start with, well, remember the cable's going to be one of them. So let's make it force 1. The other cable is going to be another force. It's going to be force 2. And then the third force is the weight coming down. And that's going to be F3. And we want to know, if it's in static equilibrium, we want to know when does F1 plus F2 plus F3 equals 0. Because that's what it meant to be at static equilibrium. Well, first thing, if we're going to figure out all these vectors, we need to know the direction angles. Remember that from yesterday? Well, the direction angle, remember, has something to do with the x-axis, and we got to make these somehow into vectors. Well, think about this. Draw a parallel line down here. And then think about it. You have a line and a line that are parallel. You have another line coming through them. Then 30 degrees is also going to be down here, because those are alternate interior angles. And think about the 45 degrees. That's going to go down there, because those are also alternate interior angles. Alternate from that side, interior of these lines. That's going to be 45 degrees. So if we're looking at the direction angle of F1, remember, it's the whole way around. So that's going to be 150 degrees. Well, next thing I'm thinking about. If I need F1 plus F2 plus F3 to equal 0, I need to know all three of those vectors, don't I? F3, by far the easiest. Look at that. F3 is coming straight down at 1,200 pounds. Well, remember, that 1,200 is the magnitude. And since it's going straight down, that's in the J direction, and it's going to be negative. So we know that F3 has to equal negative 1,200 J. Now, for F1, let's think about F1 down here for a second. F1, well, that has to equal its magnitude times the cosine of the direction angle, cosine 150 degrees I, plus the sine of the direction angle J. Sine of the direction angle J. And let's try to simplify that just a little bit. The cosine of 150 degrees is negative root 3 over 2. I. And the sine of 150 degrees is 1/2. 1/2 J. Now, we don't know what the magnitude of F1 is yet. That's what we're looking for. If you think about it, it says, what is the tension of each cable? Well, F1 was one of the cables. So we need to know what that's going to be. The way we're going to do it, let's distribute. So when I write it up here, I'm going to distribute. Force 1 has to equal, when I distribute, its magnitude 1 half J. And now let's play the same game with F2. So I'm going to come up here and play the same game with F2 real quick. F2 has to be its magnitude. This is a formula from yesterday. Times the cosine of the direction angle. Well, the direction angle for that one is just 45 degrees. So cosine 45 degrees I plus sine 45 degrees, J. And then simplify and distribute. This equals and that's what I'm going to put back up here. 2 equals now the last part. We're going to have to set up to take a substitution. But before we do that, we need to get F1 plus F2 plus F3 to equal 0. So, now remember what I said before. That means the I component has to equal 0, and the J component has to equal 0. Well, here's what I'm thinking. Start over here with F1 plus F2 plus F3, and let's look at the I component, what it would look like, and let's look at the J component, what it would look like. Well, if we have to add these up, that guy has an I, that guy has an I, this guy doesn't have an I. So we know that the I component is just going to be the magnitude of F1 times the square root, negative square root 3 over 2I plus F2, the magnitude, times root 2 over 2I. Now we know that part has to equal 0 because the I component has to equal 0. Well, let's look at the J component really quick, and we'll come back to this. For the J component, that has a J, this has a J, and that has a J. So, let's add it all up. Force 1 times 1 half J plus magnitude of force 2 times root 2 over 2 J minus 1200 J has to equal 0. Well, interesting part with these guys, because we know this is all the I component, and we know this all is the J component, we don't even need the I's, and we don't even need the J's. We just have to solve this. Now, I want to make a substitution. I'm looking at both these equations, and I'm thinking, well, which one is a smarter one to make a substitution? I'm liking the first one. My reason why, it doesn't have another number. And I'm going to be able to solve for either F1 or for F2. Now here's what I'm thinking. When you multiply this out, this guy would be, if you were to simplify just a tiny bit, negative root 3 over 2 times force 1 plus root 2 over 2 times force 2 equals 0. I'm thinking if I can add this guy over and then multiply, I have force 1 all by himself. So let's do that. So if you look, we have root 2 over 2 times the magnitude of force 2 equals root 3 over 2 times the magnitude of force 1. Now if I want to solve for force 1, I'm going to multiply by 2 over root 3. So times 2 over the square root of 3 times 2 over the square root of 3. 2's cancel. 2's cancel. And that gives me the F1, the magnitude of it, equals root 2 over root 3. We need to use this. Let me box it real quick so we all can see it. Think about a system of equations. If we know this, we can plug it in here. And then we can solve for force 2. If once we have that, we can figure out what force 1 is. And we've answered the questions. Because remember our goal. We've been doing this for a little while. Remember our goal. We want to know the tension of each cable. So we want to know what the magnitude of F1 is, and we want to know what the magnitude of F2 is. Let's plug plug in F1 down here. Here we go. We know the magnitude of F1 is root 2 over root 3. So I'm going to replace that there. Square root 2 over the square root of 3, because that is F1, times 1/2, plus the magnitude of force 2 times the square root of 2 over 2 minus 1200 equals 0. And we want to start solving for force 2. Well, first thing I'm going to do is add 1200 over. Let's multiply this out. That would give us, well, let's see. We start with root 2 over 2 root 3 plus, switch that to the front, root 2 over 2 times F, the magnitude of F2 equals 1200. And then here's what I'm thinking next. I'm thinking let's get decimals for this stuff and finish it. So, root 2 over 2 times root 3 is going to be 0.41 plus root 2 over 2 is 0.71 times the magnitude of 2 has to equal 1200. So I'm thinking if we come up here, we're going to want to subtract 0.41, subtract 0.41. That gives us that 0.71 times the magnitude of 2 equals 119,959. Divide by 0.71. Divide by 0.71. And that gives us that the magnitude of force 2 was 1,689 pounds. Now we're only halfway there. We know what force 2 is. We got to plug it back into one of those to figure out what force 1 is. So I'm thinking top equation. Plug it into that one. So remember what the top equation looked like. It said negative root 3 over 2 times force 1, magnitude of it, plus magnitude of force 2 times the root 2 over 2 equals 0. And we know that for here, we can plug in 1,689. And let's make this into decimals real quick. Let's do it all in one fell swoop. So, square root 3 over 2. 0.87. So negative 0.87 times the magnitude of force 1 plus, well, we know force 2, magnitude of it is 1,689 times root 2 over 2 is 0.71 equals 0. Let's start solving this. So negative 0.87, magnitude of force 1 plus, let's see what that comes out to. 199 equals 0. They can subtract this guy over. And then we're going to divide by him in a second. And we're going to get the magnitude of force 1 is equal to 1,378.4. 1. Remember, it was the magnitude times the cosine of 150 degrees. Remember, that's the direction angle, 150 degrees. Because that part's 30, since that was 30. And 150 plus 30 equals 180. So we get the cosine of 150 degrees I plus the sine of 150 degrees j. And it'll simplify to this down here. You should know your triangles. Here. Well, for force 2, we know that the directional has to be the 60 degrees. Because that's 60 degrees. And so fill in that the cosine of 60 degrees I plus the sine of 60 degrees j. Simplify and distribute, and you will get this down here. Now for force 3, remember, that's the force that's going straight down in the j direction. So it's negative 5,000 j. Now remember, for static equilibrium, we need the sum of the forces to equal 0. Well, then that means that the I component has to equal 0, and the j component has to equal 0. That's how you get the 0 vector. So, I added up all the i's. Negative root 3 over 2 from force 1, 1 half from force 2. This guy doesn't have any i's, so I didn't add it in there. Now, what you have to see is that I started with just that. Then I went down to here and I figured out the j component real quick. Well, I grabbed the 1 half from force 1, I grabbed the root 3 over 2 from force 2, and I grabbed the negative 5,000 from force 3, because it does have a j. And I looked at both of these equations and I said, which is going to be smarter to solve for? That one. Because we don't have the random negative 5,000. I want to try and get one of the magnitudes by itself and plug it into the other one. I saw that was negative, so I added it over. And then I thought about, well, I can multiply by 2, and that gets force 2 by itself, the magnitude of force 2, all by itself. I decided not to put that in a decimal, because I was thinking ahead, and I knew when I plugged it in down here, that the square roots would cancel, and I would want that. So that's why that's not a decimal. I found out that force 2 equals root 3 times the magnitude of force 1. Plugged it in, added it up over here. 2 times the magnitude of force 1 minus 5,000 has to equal 0. I solved for the magnitude of force 1. So the tension of the cable, the magnitude of force 1, is 2,500 pounds. Once we know that, plug it in to figure out what the magnitude of force 2 is. So I plugged in 2,500 into the top equation and solved it. And you should get the tension of force 2 is equal to 4,300